Welcome to class 7 of Deterministic Network Calculus. So last class we saw some properties of convolution, and we also saw uh, the Kleene star operator. So let me just refresh stuff about Kleene star operator. So Kleene star operator was defined on a diode. This is a complete diode. That is important. Complete diode. Uh, and for all A, for any element in the set D, A star was the Kleene star operator. So this was defined as infinite first operator of AI, where A0 equal to the unit um, element and AI is multiplication. So this unit element, so this is the unit element. So what is the property of unit element is anything the second operator performed on the unit element with any element gives the same element again. Right, so it's like a one. So one into something, you get same. Okay, next we also define the plus operator. The plus operator is similar to the Kleene star operator, where you define it as A plus. This is it's also infinite sum, but from I equal to 1 to plus infinity AI. And AI is remains same. There is no A0, directly starts from A1. A1 is A. So from these two, we had the relation between Kleene star and the plus operator as A star equal to E plus A plus, because you take out A0, then you get this, but A0 is E, so E plus A star. Similarly, A plus equal to A into A star. Right. So you take A plus, you multiply everything with A from the commutative property. You get that A into the first element E would give rise to A and so on. Right. So these two are the relations between A star and A plus. Next, we'll see some properties of Kleene star operator. So, yeah. So if the first operator and second operator is a complete diode, then one for all A comma B belongs to that set, the diode relation A comma B, if A is less than B in the diode order, then A star is less than B star in the diode order, right? And next we also want to show for all A belongs to B, right? A plus E star equal to, so the Kleene star operator of A plus E is basically A star, and the Kleene star operator of a Kleene star operator is a Kleene star operator, right? So this is somewhat like a fixed point operator. So it's somewhat like a fixed point. Next, you have A is of the diode order less than plus diode order A star, right? Proof. So the first one we'll try to prove by induction. So we'll try to prove by induction. So in the induction, we have the first case of base case. So if A is order 0, then A1 is less than B1. This is given, right? And A1 is that. Now the assumption is if A is diode order B, then AN diode order BN, right? Now we need to show as one step. Okay. So for that, what we do is we'll write out what AN plus 1 is. AN plus 1 is AN into A from this recursion. AI plus 1 equal to A into AI. Okay. And now we have a property of isotonic isotone property of the diode orders. That is, if A is diode order less than B, then A plus C is less than B plus C. Similarly, A into C is less than B into C. So these are the isotonic properties. These are the isotonic properties for the diode relation that we had described in the previous classes. We'll use these. So from the same, AN into A is less than or equal to BN into A. Okay, this is from assumption and isotonic property of diode order. Okay. Now this is diode order of cross B. Right. So this part is from the given A is less than or equal to B, and we know that the isotone property. Right. So from these two, what you get is this is A n plus 1 less than or equal to B n plus 1. Right. So if A is less than or equal to B implies if A is less than or equal to B, this implies AN is less than or equal to BN for all n belongs to n, right? Now from isotonic property of the addition, you can add all these up and you get the, so addition of all these terms, infinite sum of all these ANs give you the Kleene star operator. So adding all this up, you'll get if A is less than B implies this is the first one is done. Now second one. In the second one, first we have to show A plus C Kleene star equal to A star, right? So for that, we'll first use the definition of Kleene star operator. So this basically boils down to plus I equal to 0 to plus infinity A plus E I, right? Now what is A plus EI? Okay, so let's first write it down. A plus E0 equal to the unit element E. A plus E into 1 equal to E into A plus E, which is A plus E. Similarly, A plus E equal to A plus E into A plus E. This is A into A plus E plus A plus E. So you get A2 plus A plus C. Now here you get two A's, but since this is a complete diode, we have idempotency idempotent property of plus, right? So yeah, the idempotent property of the so idempotent semi-ring from the definition that we saw in the last class. Uh, if D and the second operator is an idempotent monoid, and the definition of idempotent was A plus A equal to A, right? If A plus A equal to A, then we say it as an idempotent. So here, that's why you have A plus A and A plus A is equal to A from the idempotent property. If you look at the example that we have seen for the min plus algebra, which is also a diode or a semi-ring, there the plus operator was replaced with min. So min is idempotent. So min of A comma A is A. So yeah, that works out. So this is it. Similarly, if you do A is 3, what you'll get is A3 plus A2 plus A plus E. Okay, so this is basically equal to plus infinity sum j equal to 0 to I. So for A2, it starts from A2 plus A plus E. For A plus E3, it starts from A3. So A3 to AI, right? So basically what you're doing here is you're doing E plus A plus E plus A square plus A plus E. Now again, using idempotent property over all the A's that each and every term would have, I can just write this as plus I equal to 0 to plus infinity AI, right? All the A's would just boil down to a single A, all the A squares will boil down to the single A square, and so on. This is basically the definition of A star. So hence proved. So here, all we used in most of the steps were from here to here, we use the definition of Kleene star operator. Right, from here to here, we used the we used idempotent property of uh, the plus operator. Same here. Okay. Next, we want to show that A star is A star, right? So now what we want to do is we want to show A star star equal to, so you get plus I greater than or equal to 0, right, over an A star. This is basically plus I greater than or equal to 0 over plus I greater than or equal to 0. So let this be J I A star I. So this is basically equal to I greater than or equal to 0. This is J greater than or equal to 0, A J plus I. That is from idempotency, you get A greater than or equal to 0 AI, which is A star. So if you apply the Kleene operator twice on the same element, you will again get back uh, A star. Okay, next we will show the order relation A less than or equal to A plus less than or equal to A star in the dioid order, right? So, left to prove A less than equal to A star, A plus, sorry, A plus less than or equal to A star in the dioid order. Okay, so first let's show A is less than A star. So when I say that I want to show A plus is less than A star, what I want to show is A plus A star equal to A star, right? And I know the uh, relation between A star and A plus. So A star I can replace with uh, E plus A plus equal to A star. And from idempotent, I get A plus E equals A star, which is basically A star equals E star, right? So this relation holds true. So which implies A plus is in the order, it is less than A star in diode order. Similarly, next we want to show A is less than A plus. So we want to show A plus is less than or equal to A plus, right? From idempotency, again, this becomes just, sorry, so this is equal to. From idempotency, this becomes equal. Therefore, this implies, so this is true. Therefore, uh, A is less than or equal to A plus. From these both, we get A is less than or equal to A plus less than or equal to A star. Okay, so yeah, we showed this theorem. Proved this theorem relations 1, 2. In the 2, we had three things. The Kleene operator for A plus E is A star. If you apply Kleene operator multiple times, uh, you will again get the Kleene operator. And the diode order for A plus, A star, and A, the relation, right? Okay, so next we have another theorem. This theorem is known as the Kleene theorem because this is why Kleene operator was actually defined. Okay, so if you have D plus into, which is a complete diode, and A comma B belongs to D, then A star B is the least solution of the affine function x equal to A into X plus B. Right. So proof. First, let's check that A star B is actually a solution or not. So if A star B is not a solution, then that can't be the least solution. Actually a solution. Let's call this 1, 2, 1, right? So what you do is you substitute A star B in place of X. If it is a solution, then you're saying that the value of X is A star B. So you take A star B, you substitute A star B in the right hand side. You get A star B into A plus B, right? This is equal to A into A star gives you A plus. That was the relation between A plus and A star. So here you'll use associativity and change the bracket from A into A star into B plus B. So this will be A plus into B plus B. And here you'll use idempotent property. So you'll get A plus E into B. So we'll take B common. So this B can be written as B into E because E is in unit and we have here. So now you take, yeah, you basically distribute it over the second operator, right? Okay. Yeah. So now we know the relation between A plus and A star. This A plus E is A star into B. So which is A star into B. So this gives you the solution to 1, right? You assume that you assumed that X equal to A star into B, and we got that A into X plus B equal to A star into B. Hence, your assumption is correct, and A star into B is actually a solution to the affine equation X equal to X plus B. Now we want to show that the the that A star B is the least solution, right? So now we'll take into account that now suppose that X is a solution of the equation 1, right? Then X equal to AX plus B. And from the dioid relation we defined in previous class, we'll get that X is greater than or equal to AX and X is greater than or equal to B. And since we have isotonian product, so we can write, since we know X greater than or equal to X, this implies X is greater than or equal to AX. Now AX is greater than or equal to A square X is greater than or equal to A3X and so on, greater than or equal to A power K X, right? But this is also greater than or equal to A power KB because X is greater than or equal to B. This last step is because X is greater than or equal to B. And yeah. Yeah, and we have X is greater than or equal to isotonian P greater than 0, AKB equal to A star B. So X will always be greater than A star B in diode order. Therefore, any x which is a solution of x equal to x plus b affine function. So any x which is a solution to ax plus b equal to x, this is the affine function, would be greater than a star b, right? Therefore, a star b, this is the least solution. So we have shown the Kleene star theorem. Okay, so next we'll go into something which we wanted to discuss. We came into to discuss, but we moved to Kleene star operator. We wanted to discuss subadditive closure. So what we do is we now try to specify the Kleene star operator for min plus functions dioid. Right. We showed in the class that the set of min plus functions, which was denoted by f, this is the set of min plus functions. And we showed that f, pointwise minimum, and the convolution operator, this forms a complete diode. Okay. So before, this is what we'll try to do. So we'll try to show the relation between the Kleene star operator for this set of diode and the subadditive closure of function. But before that, we need to know what a subadditive function is, right? So subadditive function. Subadditive function f belongs to f is subadditive if and only if. So it is both the implication. For all s comma t belongs to R plus, we have f of s plus t less than or equal to f of s plus f of t, right? This is known as subadditive function. Okay. So I'll give the definition of subadditive function again. So any function which belongs to the min plus function set, that is known to be a subadditive if for all s comma t, if f of s plus t is less than or equal to f of s plus f of t, then it is known as a subadditive function, right? Some examples of those functions are any constant function is a subadditive function. So since it is constant for all t belongs to R plus, right? So since the function is constant, so f of s plus t would be a less than or equal to, this would be a less a. A is less than or equal to a. Now this relation is natural order relation, right? Okay. So next is any linear or affine functions of the form rho plus sigma plus rho t of this one. So if you write this down, rho plus sigma t plus s less than or equal to in affine functions where rho is greater than or equal to 0. You can't fraction the negative, then you won't get. So this is less than or equal to 2 sigma plus rho t plus s. So if rho is greater than 0, 2 rho is greater than rho, satisfies. So any linear or affine functions in the form of rho plus sigma plus rho t where sigma is greater than or equal to 0. Right. The ceiling function these are also subadditive functions, right? So subadditive functions have a very unique property. That property is our subadditive functions are stable. So when it means stable, it means that if you are stable for operators like addition or convolution, but not for minimum. So when I mean stable on operators over operators or stable for operators, what I mean is if you perform addition or convolution over two subadditive functions, then the resulting solution would also be a subadditive function, right? But if you perform minimum pointwise, when I say minimum over functions, I mean pointwise minimum. So if you perform pointwise minimum over two subadditive functions, the resulting uh, function need not be a subadditive, right? So this not stable over um, pointwise minimum. Let's give an example for it. So you have let f1 be 2t. This is subadditive, right? And f2 be CLT. This is also subadditive. Right now, if I perform f1 min f2, let me call this G. I want to show that G is not subadditive, right? That will be 2t min CLT. Right now, I want to find f of 1.25. Let me find g of 1.25. Sorry, g of 1.25. This is min of 2 comma 2.5. Seal is 2. Yeah, 2.5. Okay, so this is 2, right? Now, let me find f1 of 1 plus f2 of, oh, sorry, let me find g of 1 as, let me find g of 1. G of 1 is min of 2 comma 1, which is 1, and g of 0.25, which is min of 1 comma, so add these two, you get 1.5, right? So what you get is g of 1.25 is greater than or okay, is greater than g1 plus g0.5. But from the definition of subadditivity, f of s plus t should be less than or equal to f of s plus f of t, not the other way. So here you have got the other way. Therefore, g is not subadditive function. Right. So we gave a counter example where we took two subadditive functions, did pointwise minima of that, and we saw that g was not a subadditive function. Right. Okay. Next, we'll see some properties of subadditive function, which we have just stated. So mm, let f comma g be two subadditive functions. Then one f plus g is subadditive. star F convolution G is also subadditive. Right. So we'll do the proof. So F comma G, these are subadditive functions. For all S comma T greater than or equal to 0, we will do F plus G at S plus T. We are calculating F plus G at S plus T. This is F of S plus T plus G of S plus T. But since F is a subadditive function, this is plus G of S plus G of T. And this is less than or equal to F plus G at S plus F plus G at T, right? Clumping these two and these two. So yeah, from here you've got that F of F plus G at S plus T is less than or equal to F plus G at S and F plus G at T. Therefore, F plus G is subadditive, right? So second is convolution. So what we want to find is um, so for convolution we'll do the reverse. So we'll do F convolution G plus at S F convolution G at T, right? So we'll write the definition 0 less than. Okay, we'll write the second definition of convolution which we have heard, which is U plus V equal to S FU plus GV plus inf W plus Z equal to T FW plus GZ. Okay, so now this is greater than or equal to inf. I'm taking everything in the same bracket and U plus V equal to S and W plus Z equal to T FU plus GV plus FW plus GZ. And then from since F and G are subadditive, FU plus W plus GV plus W. Right, now replace U plus W and V plus W with X and Y. Then you get greater than or equal to inf X plus Y is equal to S plus T Fx plus Gy. This is basically F convolution G at S plus T. So we have found that F convolution G at S plus T is less than or equal to F convolution G at S and plus F convolution G at T. Therefore, F convolution G is a subadditive function, right? So today we'll define subadditive closure and then we'll stop for today. Then we will come and see some properties of subadditive closure. Okay. So, definition of subadditive closure operator. Right. So let f be a function in the f. So f okay, I'll define the subadditive closure operator with the same uh, notation that I've used for Kleene operator because you'll see that it is almost the same thing. So it's the minimum over I equal to 0 to plus infinity fi, where f0 equal to e fi plus 1 equal to f convolution fi. Okay, so it's basically the Kleene star operator on on the dioid f min, pointwise min, and convolution. We have shown that this is a diode, right? Yeah, so this is the Kleene star operator on the diode f min convolution. Okay, so yeah, we'll stop here for today. So what we discussed today was we discussed some properties of Kleene star operator. This was one set of properties with Kleene star operator. Then we discussed the Kleene star theorem, where we said that A star B is the least solution for the affine equations x equal to x plus b. Right. Then we saw subadditive closures. Then we defined what a subadditive function is. We saw some properties of subadditive functions. It is stable in plus and convolution, but not stable in pointwise minimum. We showed why it is stable in addition and convolution. Next, we defined the operator subadditive closure operator. The subadditive closure operator is basically Kleene star operator in the dyad of min plus functions, with the first operator as min and second operator as convolution. Okay, so yeah, I'll stop my class here. Thank you.